ball is 10, but since I kick it at an angle, I can't assume that that's x or y. Okay? Its total velocity is 10 meters per second. So find the maximum height it can reach. So we're looking for delta h, or something for h would be delta y at one point. The horizontal displacement, how far it goes horizontally, and the total time required for this motion. Now, first thing we got to do is we got to take our velocity and break it up and do some component, break it up into things. So here we go. Got a ball. Let's draw a ball now. Got a ball. And we kick it at some angle. That angle is 53 degrees with the horizontal. And that means its velocity is 10 meters per second, right? How would I find my x and y components or parts that make up that triangle? So check it out, and everybody's going to have to start playing some bells and whistles here in a second. Initial velocity in the x direction, and we also have initial velocity in the y direction, right? What trig function would you like to use to find initial velocity in the y? Well, that would be opposite over hypotenuse, right? What's that? Sine. So, sine of my angle is opposite over hypotenuse, SOHCAHTOA. Right. On your reference sheet, the Pythagorean theorem, and next to that is the SOHCAHTOA, your trig functions. So this would be sine of 53 equals opposite over hypotenuse, which is 10. So my initial velocity in the y direction is going to be 10 sine 53. Feeling okay there? All right. Again, reading this stuff is ugly. But once you know what to do, it's you're like, oh, this just feels like plug and chug, and that's really what it is. Okay. However, we have to break a muscle. What unit is this in? X pre-calc, people. Degrees. So what mode should your calculator be in?
Exactly degrees.
Degree mode. Okay. So grab a graphic calculator. Let's check it out. We got to switch our calculator to degree mode. Now we do have to develop the skill set because pre-calculus and calculus, you're going to be switching your calculators to radian. We got to switch it to degree. So I do need to be pretty vigilant on making sure which one you got. So 3 in the back. Click on mode. The 4th option down, go over to degree and hit enter. It'll switch it to degree mode.
We use radian.
After this class, then. Ten sine 53. So my initial velocity in the y direction. 2 decimal places will absolutely carry you enough. 7.99 meters per second. Everybody get the same number at? Just plug a choke in your calculator. Alice.
The spirit is still here.
We good here for initial velocity in the y? Let's switch now and let's go over to do the x. So if we're looking for initial velocity in the x direction, that pink arrow, What trig function would we want to use? They Reese?
Cosine.
Cosine. Because we have adjacent over hypotenuse. Are you guys with the sine, cosine, tangent? You guys good? Like opposite over adjacent, things like that? Okay. I just made that assumption, but I didn't really ask. I'm going to have to check in on that. So, cosine theta equals adjacent over hypotenuse. So cosine of 53 equals initial velocity in the x direction times 10. So 10 cosine 53. Can I show you a neat little shortcut? If you press the up arrow, your calculator will highlight a segment. If we want to repeat something we've done before, but just change a number or change a variable or change something, we can actually just highlight over it, hit enter. It'll bring it on down. I just go over to sine now, say cosine. 6.0102 meters per second.
Isn't this exactly what we did with the bridge last year in engineering?
Yes, we've broken into components, absolutely. And you're going to see more of that when we do forces. Is that unit 2? It's going to you're like, this feels, you're like, whoa, deja vu. This feels very familiar. Very familiar.
Very filament.
Very filament, yes.
Are we doing bridge math and engineering then?
No. Bridge math is behind you,
Thank you.
except for John. Okay. All right. I'm going to take that picture. I'm going to disappear so I can start writing my information. Here's what we know. We know initial velocity. I'm going to bump up that thickness. We know initial velocity in the x direction is 6.02. We know initial velocity in the y direction is going to be 7.99. If you guys remember, what did I say yesterday for projectile problems? 99% of the time, what's the first variable we should try to look for? Time. So we're going to look for time. All right? What other things do we know also about projectile motion? What still exists always?
Gravity.
Gravity. So what's acceleration in the y direction?
9.8.
Negative 9.8, right? Acceleration in the y direction? Negative 9.8 meters per second squared. What about acceleration in the x direction? Is our ball attached to a rocket? Just give it to me, Carter. Just tell me.
Oh, no, I have a question.
What's your question?
So, you said negative 9.8 for gravity, but didn't you say like a couple of days ago that we could use negative 10?
You can use negative 10. Negative 10 is absolutely okay, rounded number. Okay? So, I think reset. Did you say 0? 0, right? Because when we kick our ball, it's not attached to a rocket. There's nobody in the midair pushing on it. It's done in the x direction. So that's 0. I'm going to come back to my picture real quick. We're going to zoom in. I'm going to draw on it. Let's do this in red. Let's do pink. I'm feeling pink today. Projectiles make a parabolic motion. Do you see that? Parabolic motion. Okay. If we try to use, and I don't want to waste my time here. I don't want to waste your time or waste my time. If we try to use our kinematics equations to find time, you're going to find out that there are 2 moments in time that the ball's on the ground. At time equals 0, right? At time equals 0, and whatever that time is. If we use our kinematics equations, you're going to find out time equals 0. Everybody's going to prove that the ball was on the ground to begin with. That's a waste of our time. However, we can break this problem up to something we can find. And that is going to have to deal with this halfway mark. So we call that T1 half. Because if I know half the time, what would I do to find the whole time? Double. That's it. Okay. We also know one other piece of information. What is the velocity in the y direction at the halfway point? That's the acceleration. The velocity. So I'm going to get my ball. Okay. Throw the ball up. Like that. The whole path, right? At the very tip top. What's the velocity? 0. For all projectile motions. T1 half, your initial your velocity at the halfway point in the y direction is 0. Okay, so I'm going to add this to my information I have when we roll zoomed in. Over here, I'm going to do velocity in the y direction at the halfway point equals 0. We're just full of noises today. Does that thing go off every day?
Yes.
I feel like it's just some days.
I feel like it's some days.
Okay. All right, let's check it out. I'll give you a hint. Let's highlight it. Could I use the information I have now to find T1 half? Is there one of my kinematics equations that I could use to find T1 half now? One, right? I don't know anything about height. I don't know anything about it, so I can't use 2 or 3. So check this out. I'm going to rewrite that first equation. And then we're going to make it pretty. We're going to dress it up. Velocity final equals velocity initial. Acceleration times time. Instead of velocity final, we can rewrite it as velocity in the y at the halfway point, right? Equals velocity initial at the y direction plus acceleration, which is negative 9.8, times t 1 half. Can I find t 1 half now? Sure. That's going to be 0. Equals 7.99 minus 9.8 T1 half. I do not have this number memorized. .99 divided by 9.8. I get my halfway time is 0.815. So how would I find full T? Multiply by 2, right? So I'm going to go back over here. I'm just going to multiply my number by 2. So my full time is 1.63 seconds. Let's make sure I've figured out my routing. are we looking for again? What's the big question to look for? How high it went versus how far it went? What's up, Reese?
Got something different.
You got something different. What'd you get?
For time at 1/2, I got 0.925.
Well, you put the 9.8 to the other side and you divide by 9.8.
Huh?
So 9.8 T 1/2 equals 7.99. And you divide by 9.8. That would get you that 0.8, whatever number that was. 0.815. Okay. Time is the key to making this problem work. Right? It's the big key. It's the big bambino. It's the big problem. Because now I know enough information to find my delta y and my delta x. But I'm asked one quick question before we start plugging and chugging away. Can we agree to find my delta x here? I would use my full time interval. What would I use to find my delta y?
1/2.
You'd have to use your half time interval. What number would you get for your delta y if you used the full time? 0, because the ball's on the ground. At 1.63 seconds, the ball's on the ground. So to find delta y, we have to use our halfway time. So delta y equals initial velocity in the y direction times time. But t 1/2 for delta x, we use the full time. One half a t squared. See what you get for delta y and delta x. Here's what I'm talking off a whisper. It's not like there's secrets here. Secrets don't make friends.
Leaves these two equations height and horizontal displacement.
What do you guys get for delta y? You guys get any numbers yet? It's okay to say no. Okay. Delta y equals initial velocity in the y direction is like 7.99 times 0.815. I'm running out of space. Plus 1/2 negative 9.8 1.6, nope, wrong time. 0.815 squared. This is close to rocket science. We actually derive the rocket equation of how fast a rocket needs to go to leave planet Earth.
Great, so now we are getting into the realm of
When we finish energy, unit 3, no, unit 5, we'll derive the rocket equation. How fast an object has to go to leave planet Earth.
How fast?
There's gonna be a lot of rocket science jokes.
Come on, man, it's not rocket science. Just close to it.
Until it is.
Just close to it. I want you guys to know, this stuff was in my brain when we're teaching ICPs. I miss those easy days.
So you complained about torturing us about rocket science since ICP.
Yep.
Thanks.
Way back in the day, I was looking at you guys as 8th graders. We 8th graders. I'm going, you're going to learn rocket stuff. 9.77 meters. Initial velocity in the x direction. What was that number? It was like 6 point something, right? 6.02. I love stuff in the x direction. Somebody know why? Because acceleration is 0. You don't have to do anything. 6.02 times 1.63. Delta x equals 9.81. We'll leave it there. I'll leave it right there. That's a little too small. I'll leave it right. Actually, here's what I'll do. We'll condense this. We'll put all this stuff right here. All this stuff right there. And I'll do that. By no means do I expect to be pros at this question today. And we're going to do some practice here in a second, here in a moment. Okay. This is the crux, the toughest part of solving it. Projectile at an angle.